My name is Prince Matthew, and today I'll be talking about learning deterministic one-counter automata. So the full version of this work will appear in the proceedings of LICS 2025. You can also find the link to the archive version here. So this is a joint work with Dr. Vasukalan from University of Porto and Dr. A.B. Srijit from IIT Goa. So before starting the talk, let's first look at what a one-counter automata is. One can think of it as a finite state machine that have access to a counter. So it reads from a one-by read-only input tape. On reading a symbol from the input tape, the finite state machine can increment or decrement the counter by 1. It can also check whether the counter value is 0 or not before taking a transition. This essentially means that the finite state machine here has two sets of transitions, one for counter value 0 and the other for positive counter value. Note that the counter can never go below 0 on taking a transition. So this is a one-counter automata accepting the language A raised to n, B raised to n, A. We have three states, P, Q and R. P is the initial state and R the final state. This transition here can be taken on reading a P if your counter value is greater than 0 and it decrements the counter by 1. This transition from Q to R can be taken on reading an A if your counter value is equal to 0 and it decrements the counter by 1. Okay. So let's say if you had A raised to n, B raised to n, A in your input tape, on the initial set of A's you would increment your counter. On encountering the first B, you would move from the state P to Q and you would decrement your counter. On the successive B's, you would decrement the counter by 1. So if you have seen equal number of A's and B's initially, then your counter would become 0. And then on the last day, you check for counter value equal to 0. Okay. And then you increment the counter and go to the final state. So the word A raised to n, B raised to n, A would be accepted by this machine. So what we are interested in is active learning of one-counter automata. So in an active learning framework, you have a learner and a teacher. So in our setting, we assume that the teacher knows a DOCA T. The learner's aim is to learn a DOCA L equivalent to T. The learner can query the teacher, and based on the teacher's response, the learner tries to construct a automata L that is equivalent to T. So in our setting, the learner can ask two kinds of questions to the teacher. So the first one is membership query, where the learner gives the teacher a word W and asks whether W is in the language of T. The teacher responds yes or no. The second is minimal equivalence query, where the learner presents the teacher a DOCA L and asks whether L is equivalent to T. The teacher responds yes if they are equivalent, or no and a minimal counterexample that distinguishes L and T. So this is the minimal word that's in the symmetric difference of the languages of L and T. So let's take a brief look at the existing literature. In 87, Anglin proposed a learning algorithm for DFA using membership and equivalence query that runs in polynomial time. This is the famous L-star algorithm. In 95, Fami and Roos gave a learning algorithm for determining real-time one-counter automata using membership and minimal equivalence query that run in EXP time. It also required exponential number of queries. Later in 2010, Nader and Loading had a learning algorithm for visibly one-counter automata using membership and minimal equivalence query that again was running in exponential time. In 2022, Brure, Pere and Strake gave an algorithm for learning deterministic real-time one-counter automata using membership, minimal equivalence and counter value query. So what is a counter value query? For a counter value query, the learner presents a teacher a word W and asks what is the counter value reached on reading that word W in the teacher's machine. The teacher returns the corresponding counter value. So in this setting, they showed that DROCA again can be learned in exponential time and exponential number of queries. So in 2025, we had a learning algorithm for deterministic real-time one-counter automata. So we showed that DROCA can be learned using membership, minimal equivalence and counter value query in exponential time using polynomial mini queries. So all the existing works required exponential time and exponential number of queries. So in this work, we show that you only require polynomial number of queries. So the next question that naturally one would ask is, can we do better? So in this talk, I'll present OL star, which is a learning algorithm for deterministic one-counter automata that runs in polynomial time using membership and minimal equivalence query. So the theorem would be as follows. If the teacher knows a language recognized by a DOCA T, then the all-star algorithm learns a DOCA L that is equivalent to T in time polynomial in the size of T using membership and minimal equivalence queries. So what are the assumptions that we have? We assume that the teacher knows a language accepted by a DOCA T, and for the rest of the talk we denote by n the size of T. And to make this presentation simpler, we assume that there are no epsilon transitions in T and the counter value is always incremented or decremented by at most 1. So the learner's aim is to learn a DOCA L that is equivalent to T. All-star algorithm proceeds in 6 steps. The first step is learning a K behavior DFA. Now, what is a K behavior DFA? DFA A is a K behavior DFA of DOCA T if A is K equivalent to T. That is, a word W is accepted by A if and only if W is accepted by T for all words of length less than or equal to K. One can use the LICS algorithm for learning a K behavior DFA in polynomial time in K and N. So this is done using membership and minimal equivalence score. So the learner's first step is to learn a poly n behavioral DFA. So we will fix what this poly n is towards the end of the talk. So this is a polynomial in n. The second step of the OSL algorithm is to partition the states of this behavior DFA. So the DFA is partitioned into three: initial region, border region, and region of interest. Initial region are all states reachable by words of length less than n raised to 4. The border region contains states reachable by words of length n raised to 4 but not less. And the region of interest contains all the remaining states. Okay. So first we learned the behavior DFA, then we partition the states of the behavior DFA. Now what is next? So now the learner constructs a partial OCA for all border states and then combine all these partial OCA to get a final OCA. Okay. So how do we construct a partial OCA for all border states? This is a crucial part of the construction and we will take a look at it. So towards this purpose, we will first identify winning sequences. So we say that a sequence of words W0, W1, W2 up to Wk is a winning sequence for a state P. The run of these words on the DOCA T reach configurations Pi, Pi plus T, Pi plus 2D and so on. Okay. So they all reach the same state, but the counter values differ by D. Now the winning sequence lemma says that for any state P0 in the behavior DFA A, one can enumerate polynomially many sequences of the form W0, W1 up to Wk in polynomial time such that one of them is a winning sequence for P0. So this is a very crucial part of the algorithm, and for identifying these winning sequences we use the property of the length lexicographically minimal reachability witness that reaches configurations in a one-counter automata. Now consider a winning sequence W0, W1 up to Wk. You run these words on the behavior DFA. So we will reach some states P0, P1, P2 up to Pk. Now the next step is to run a parallel BFS from this sequence. So we will identify all distinct sequences and we prove that there are at most n cube such distinct sequences. So these sequences will form the states of the DOCA that we construct. So we will see an example and you will have a better understanding. So let's say you are starting from the sequence P0, P1 up to Pk. Okay. So this is the first winning sequence that we have identified. Now you run a parallel breadth search from this. So you read A simultaneously from all of the states. Let's say you reach another sequence of states. Let's say you reach Q0 to Qk. So in the partial OCA that you are going to construct, you will have one state corresponding to this sequence, which is P, and here corresponding this sequence, you will have another state Q. Okay. So here from P0 on an A, you are going to Q0. From P1 on an A, you are going to Q1 and so on. So from the state P in the partial OCA, you will have a transition on A greater than or equal to 0 with counteraction 0 that goes to Q. Okay. So once this algorithm proceeds, you will kind of see how this works. Now let's say you read a B from P0 to Pk and you reach another sequence, let's say R0 to Rk. Then you would have a transition from P to R on a B when the counter value is greater than or equal to 0 with counteraction 0. So now you will read an A from Q0 to Qk. So let's say you reach another sequence T0 to Tk. So in the partial OCA you would have a transition from Q to T on A greater than or equal to 0 with counteraction 0. Here now comes the interesting part. Let's say on a B from Q0 to Qk you are reaching the states R-1 to Rk-1. So Q0 goes to some state here, Q1 goes to R0 here, Qk goes to Rk-1 and so on. Okay. So now what would be the transition in the partial OCA that you construct? So from here on a B greater than 0, you will have a transition that goes from Q to R, which decrements the counter by 1. Since you can't decrement below 0, the transition from Q on a B equal to 0 is not defined for now. Okay. Now what happens if you read an A from R0 to Rk? Let's say you go to T1 to Tk plus 1, some state here. Then in the partial OCA that you construct, you will have a transition from R on A greater than or equal to 0, which increments the counter by 1 because R0 goes to T1, R1 goes to T2 and so on. Now let's say, yeah, you had a self loop here, you'd have a self loop there, you have a self loop on an A there, you'd have a self loop on an A there. Now let's say on reading a B from this T0 to Tk, let's say you reached states R2, Tk goes to Rk plus 2 or something. Okay, so then in the corresponding partial OCA, you'd have a transition from T on B greater than or equal to 0, which increments the counter by 2. But it can at most be some 2 times n. So the parallel BFS colors most of the reachable state from a border state, but up to some polynomially many states are not colored. For example, the R minus 1 in the previous example, and some states reachable from R minus 1. However, these states are added to the partial OCA with 0 counter value. So the initial region is also added to the partial OCA with the 0 counter value to obtain a partial OCA for the border state. So here you saw that transition from Q on B equal to 0 was not defined because it goes to a minus 1 state. And also, let's say if you had a transition from R minus 1 which goes to P0 and T0, the transitions were also not present in the partial OCA. So what will you do? You will add this additional state R minus 1 here. So this state will always be reached with counter value 0. So from Q on B equal to 0, you will go to the state R minus 1. Okay, so the state with counter value 0. And from this state on a B, you would go to the state P with counter action 0, and to state T on reading an A with counter action 0. Okay. So step 6 of the learning algorithm is to take the union of the partial OCAs corresponding to all the border states and the DFA corresponding to the initial region. So the size of this counter automata L is some order of n raised to 8. And from the equivalence result of Bohm, Keller and Younger, you know that there exists a polynomial n such that if L is poly n equivalent to T, then L and T are equivalent. Okay. Now we show that the constructed OCA L is indeed equivalent to the teacher's OCA. So the poly n behavioral DFA that we initially constructed, the poly n is actually the poly n that comes from the equivalence result. Okay. So by the correctness of the construction in the last step, we know that the constructed OCA L is poly n equivalent to the behavioral DFA A. The behavioral DFA A is indeed poly n equivalent to T because A was the poly n behavioral DFA of T. Okay. And now we get that L is poly n equivalent to T from the above two steps. And from the equivalence result, you get that therefore L is indeed equivalent to T. So in summary, what are the steps that we had? So initially we construct a poly n behavioral DFA using the LICS algorithm. We partition the behavioral DFA into initial region, border region, and border region of interest. And for each border state, you generated winning sequences of words W1 up to Wk. You ran these words on DFA to get a sequence of states P0 to Pk. You ran a parallel BFS from the sequence, and all reachable sequence of parallel BFS form states in the partial OCA. The counter values are incremented or decremented based on the shift in the sequence. You add the mid state and the initial region to get partial OCAs. Finally, you take union of all these partial OCAs to get the final OCA. Okay. So in conclusion, the All-Star algorithm learns a DOCA equivalent to the teacher's DOCA using membership and minimal equivalence queries in polynomial time in the size of the smallest DOCA recognized in the language. As a corollary, we also have a polynomial time algorithm for polynomial approximation for minimization of DOCA. So if you have a DOCA, you can find another DOCA whose size is at most polynomially larger to the size of the minimal DOCA recognizing the language in polynomial time. So as a future work, one can think of replacing the minimal equivalence query with equivalence query. Also, one can think of designing a practical version of the All-Star algorithm. So even though the algorithm All-Star runs in polynomial time, the involved polynomials are huge and cannot be used in practice. So another direction of future research is improving the running time of equivalence checking of one-counter automata. So right now the equivalence check is in polynomial time, but again the involved polynomials are huge, and these polynomials have a direct impact on the running time of the All-Star algorithm. So if you have a faster algorithm for checking the equivalence of one-counter automata, you would have a faster algorithm for learning as well. Also, learning weighted models like weighted visibly one-counter automata is another future work that one can think of. If you have any questions, please write to me. I will be happy to respond. Thank you.